Good afternoon, everyone. My name is Dr. Christopher Moore, and I'm a research associate at West Virginia University, and I lead the day-to-day operations of our grant-funded pollution prevention team. Our team provides no-cost pollution prevention assessments and other related technical support to businesses within West Virginia. Today, I'll be presenting the fourth webinar of our five-part series covering the EPA national emphasis areas. Pollution prevention best practices for the aerospace product and parts manufacturing and maintenance industries. In this webinar, I'll first provide a brief introduction into pollution prevention as defined by the Environmental Protection Agency and what activities are and aren't considered pollution prevention. Next, I will discuss EPA's national emphasis areas, which are prioritized industries under EPA's pollution prevention initiative. The main focus of this webinar, however, will be the fourth national emphasis area, which is aerospace products and parts manufacturing and maintenance. I'll provide some background into the industry, then cover several pollution prevention best practices that can be implemented by facilities within those industries to minimize their environmental impact and cut pollution at the source. Then, after a brief summary, I'll do my best to answer any questions you have. If you have any questions along the way, feel free to send them in the chat and I will address them after the presentation. So let's get started. Before diving into the topic of pollution prevention, we first need to understand pollution. Pollution, according to the Oxford Dictionary, is the introduction into the environment of a substance or thing that has harmful or poisonous effects. Pollution has far-reaching consequences, not only affecting human health, but also disrupting ecosystems and threatening biodiversity. Given these impacts, it's clear that immediate action is needed to reduce pollution and its adverse effects. Pollution prevention, as defined by the U.S. Environmental Protection Agency, refers to any practice that reduces, eliminates, or prevents pollution at its source before it is created. This approach differs from pollution control, which typically deals with managing pollution after it has been generated. Instead, P2 focuses on proactive steps to prevent waste and pollution from occurring in the first place. This hierarchy of pollution management shows a step-by-step approach to managing pollution, starting with the most desirable actions at the top and moving down to the least preferred options at the bottom. When possible, the creation of pollution should be prevented in the first place. If the creation of a pollutant can't be completely prevented, the next objective should be to reduce the amount that is created. When the amount of a pollutant can't be feasibly reduced, options to reuse or recycle should be explored. The next step, recover, refers to the process of extracting any useful material or energy from the waste. The least preferred option is disposal, where the waste will go to a landfill or otherwise be released out into the environment. EPA's Pollution Prevention Initiative emphasizes this hierarchy, encouraging a primary goal of preventing and reducing pollution at its source. So as part of the EPA's Pollution Prevention Initiative in 2015, several priority sectors known as national emphasis areas were identified. These 6 sectors were identified as priorities by the EPA Pollution Prevention Program to focus resources and efforts for maximum environmental and economic impact. These sectors offer substantial P2 opportunities and create a focused approach that allows for better resource allocation and the ability to share successful strategies across similar industries. The original 5 NEAs were the food and beverage manufacturing and processing, chemical manufacturing, processing, and formulation, automotive manufacturing and maintenance, aerospace product and parts manufacturing and maintenance, and metal manufacturing and fabrication. A 6th national emphasis area was established several years ago. Instead of focusing on a specific industry sector, the EPA realized the need of assistance with pollution prevention on tribal and native lands within the country. The focus of the discussion today, though, will be on the 4th national emphasis area, aerospace product and parts manufacturing and maintenance industries. The aerospace products and parts sector includes industries classified under the NEAs industrial classification codes, beginning with 3364 for manufacturing, and 488,190 for maintenance. In 2020, there were over 1,773 establishments within this sector, with 269 of them, or about 15%, reporting to the toxics release inventory. The chart shows the volume of waste managed by different approaches from 2011 to 2020 within this industry. The amount of waste was on an upward trend prior to 2020 when the pandemic had a significant effect on their sector. While most of the waste was managed by recycling or energy recovery over this period, a significant portion of the waste was treated or disposed with no sign of reduction. There is still a lot of opportunity for improvement utilizing pollution prevention methods. There are numerous industries within the aerospace product and parts sector, encompassing a wide range of industries. The industries within the sector can be grouped into 7 different categories: aircraft manufacturing, aircraft engine and engine parts manufacturing, other aircraft parts and auxiliary equipment manufacturing, guided missile and space vehicle manufacturing, guided missile and space vehicle propulsion units and parts manufacturing, other guided missile and space vehicle parts and auxiliary equipment manufacturing, and other support activities for air transportation. So now that we've explored the variety of industries within the sector, let's move towards discussing some of the P2 best practices within the sector. These best practices that we'll be discussing can be broadly classified into 3 categories. First, we'll discuss a few practices related to material substitution and alternatives. Then we'll explore a few practices related to wastewater management. And finally, we'll look at how eco-friendly products can be implemented in this sector. So first, let's look at some P2 best practices related to material substitution and alternatives. There'll be 3 best practices covered: replacing hazardous chemical-based sealant removal products with non-hazardous alternatives, substituting metal parts with more sustainable composite parts, and substituting hexavalent chromium with trivalent chromium in metal plating. So sealants play a critical role within this sector. They're used to seal gaps, to prevent leaks, provide additional stability between parts, and protect against corrosion, among other things. Often when repairs or maintenance must be performed, the sealant must be removed or replaced. Chemical-based sealant removal products are often used to remove sealants. The first P2 best practice we'll discuss involves substituting these chemical-based sealant removal products with non-hazardous options. So toluene methyl chloride and N-propyl bromide are among the hazardous chemicals commonly found in these sealant removal products. While each of these are very effective in breaking down sealants, each of these have potential effects on human health and the environment. Toluene, for example, is a volatile organic compound posing environmental risk through the contamination of air and water. It contributes to air pollution, impacts water quality, and contributes to ozone formation. Exposure can have serious health consequences. It is a neurotoxin, which means prolonged exposure can cause damage to the nervous system, leading to cognitive impairment, kidney necrosis, and even cerebral atrophy. Next, methylene chloride, another common ingredient in sealant removal products, can contaminate the air, water, and soil, disrupting ecosystems. Methylene chloride is a potential carcinogen, meaning it has been linked to cancer in humans. Additionally, it can cause skin irritation and respiratory issues, making it a significant health hazard, especially in poorly ventilated work environments. And third, N-propyl bromide also is classified as a volatile organic compound, and in 2022 was added to the EPA's list of regulated hazardous air pollutants under the Clean Water Act. When water is present, N-propyl bromide slowly reacts, forming corrosive acids. And from a health impact standpoint, N-propyl bromide is particularly concerning because it is harmful to the nervous system and can lead to liver toxicity with repeated exposure. These chemicals not only pose risks to workers handling them, but also contribute to environmental pollution. So it is the benefit of all to explore alternatives for such hazardous chemical containing sealant removal products. So fortunately, there are alternatives available that are safer for the environment and human health. A few of the available options are Polygon 310 AG, Diastone DL, and Skylene 1000. Polygon 310 AG is an aviation-grade polysulfide stripper designed to seep into cured sealants, dissolve them, and convert them into a liquid. Once broken down, the sealant is suspended to prevent redeposition, allowing for easy rinsing. Diastone DL provides powerful solvent action while eliminating exposure to hazardous chemicals, making it a safer and effective choice for aerospace maintenance. And Skylene 1000 is an environmentally friendly sealant remover that efficiently breaks down sealants while being biodegradable and safe for workers. So these alternatives not only break down and dissolve sealants efficiently, but they also prevent redeposition, making cleanup easier. And most importantly, they're designed with worker safety in mind and are less hazardous to human health and the environment compared to traditional solvent-based sealant removal products. So there are several benefits of switching to a non-hazardous sealant removal product. First, unlike sealant removal products with hazardous chemicals, these alternatives reduce toxic emissions, minimize hazardous waste, and lower environmental contamination, making them a more sustainable choice. Next, by using safer alternatives, employees will have reduced exposure to neurotoxins, carcinogens, and other hazardous substances, creating a healthier work environment. Furthermore, since many of the hazardous sealant removal products include chemicals that are regulated, which may require additional resource use to maintain compliance. Furthermore, these safer alternatives make compliance with standards from OSHA, the EPA, and REACH easier. These alternatives help companies stay compliant. These alternatives are also designed to work as well or better than their hazardous counterparts. They break down sealants effectively while also preventing redeposition, allowing for easier cleanup. These improvements can lead to faster turnaround times, increased productivity, and improved maintenance efficiency. The aerospace industry, moving on, the aerospace industry relies heavily on metals in the manufacturing of products. The next best practice we'll cover is substituting metal parts with composite parts. So metal extraction and processing require large-scale mining operations, which lead to land degradation. Open pit mines strip away vast areas of land, disrupting ecosystems and making land recovery extremely difficult. Another major consequence of metal extraction is water pollution. The extraction and refining of metals releases harmful chemicals and heavy metals into nearby water sources. And toxic runoff, as seen in the image on the left, contaminates rivers and groundwater, endangering both wildlife and human populations. Additionally, mining activities contribute to the loss of natural habitats. Forests and ecosystems are destroyed to access metal deposits, leading to biodiversity loss and long-term ecological imbalances. And beyond these direct impacts, metal production is also a major source of greenhouse gas emissions, further contributing to climate change. The process of extracting, refining, and transporting metals consumes enormous amounts of energy, mostly from fossil fuels. So one potential solution is using composite materials instead of metal when engineering and manufacturing parts. So there are composites like carbon fiber reinforced polymer and glass fiber reinforced polymer, which are plastics that are reinforced with fibers made of carbon fiber or glass fiber. These composites offer numerous advantages over metal when manufacturing aerospace parts and products. One of the biggest advantages of composites is that they are lightweight. In aerospace applications, weight plays a critical role in fuel efficiency. Using lighter materials directly translates to lower fuel consumption and reduced greenhouse gas emissions, making composite-based aircraft more environmentally friendly. Despite being lightweight, they're also highly durable. Unlike metals, which suffer from fatigue and corrosion over time, composites maintain their structural integrity for longer periods, which leads to reduced maintenance, lower replacement costs, and overall improved operational efficiency. Additionally, composites require less energy to manufacture compared to metals. Extracting and refining metals is an energy-intensive process that releases large amounts of carbon emissions. By switching to composite materials, energy consumption and environmental impact of aircraft production, can be reduced. Furthermore, composites are corrosion resistant. Metals often degrade due to oxidation and exposure to harsh environmental conditions, whereas composites are naturally resistant to such damage. This enhances aircraft longevity and reliability, reducing the need for frequent repairs and replacements. And finally, composites offer design flexibility, allowing for the fabrication of intricate, aerodynamically efficient shapes. This helps in optimizing aircraft performance while ensuring maximum strength and safety. So let's summarize the benefits of using composites instead of metals in product manufacturing. First, there's a reduced environmental impact. Not only do these composites reduce the need for metal production, which involves mining, refining, and large-scale emissions, but composites also provide the environmental benefits of improved fuel efficiency of the products they are used in. A shift to composites significantly decreases the carbon footprint of industries within this sector. Second, composites are less energy intensive. Metal extraction and processing require substantial amounts of energy, while composite manufacturing is more efficient, consuming less energy and water. Third, since they are resistant to fatigue, corrosion, and harsh environmental conditions, they require less maintenance and fewer replacements over time. Parts made of composites can have a longer lifespan than their metal counterparts. Finally, while composite materials may have a higher initial cost, their durability, lightweight nature, and reduced maintenance requirements make them a more economical choice in the long run. Improved fuel efficiency, lower repair costs, and extended service life all contribute to significant financial benefits over the lifespan of the product. Now moving on. The next P2 best practice that can be implemented into metal plating processes is replacement of hexavalent chromium with trivalent chromium. So metal plating is crucial in the aerospace industry. It provides benefits including corrosion resistance, strength, and temperature resistance to the parts. Hexavalent chromium is commonly used in metal plating and has a main ingredient of chromium trioxide. However, hexavalent chromium has several risks. First, hexavalent chromium contributes to air, water, and soil contamination, leading to long-term ecological damage. The waste from hexavalent chromium plating contains dangerous substances like lead chromates and barium sulfate and must be treated as hazardous waste, which makes disposal costly and complex. Along with the environmental risks, there are also health risks associated with hexavalent chromium exposure. Even low-level exposures can cause skin irritation, organ damage, and chronic illnesses. Additionally, it is a known carcinogen, posing serious health risks such as lung cancer and respiratory diseases for exposed workers. Since metal plating is so essential to the industry, eliminating these processes is not reasonable. But trivalent chromium may be a viable alternative to hexavalent chromium. Trivalent chromium does have higher material costs and can be more difficult to work with, but overall the pros outweigh the cons. First, trivalent chromium plating can provide the same high-quality chrome finish as hexavalent chromium with excellent durability and corrosion resistance. Trivalent chromium plating uses chromium sulfate or chromium chloride as the main ingredient instead of chromium trioxide, which makes trivalent chromium less toxic than hexavalent chromium, which protects the health of the workers. Next, trivalent chromium produces less hazardous waste. This means easier disposal, lower costs, and a reduced environmental footprint. Plus, trivalent chromium offers more color options than traditional hexavalent chromium plating, like black and blue, And this gives manufacturers greater flexibility with the final parts. Therefore, by switching from hexavalent chromium to trivalent chromium plating, there will be a lower environmental impact. With fewer hazardous byproducts, it reduces pollution and waste disposal will be easier. Next, worker safety is increased as trivalent chromium is not a known carcinogen and has lower toxicity. Additionally, it helps with regulatory compliance. There are currently less regulations on trivalent chromium than hexavalent chromium. And finally, it offers cost savings in waste management. Since it generates less hazardous waste, businesses can reduce disposal costs and complexity. Next, we'll look at some best practices in this sector that are related to wastewater management. The three best practices we'll discuss are going to be using diffusion dialysis acid recovery systems, using filtration along with regular spiking to extend acid bath life, and implementing an ultrafiltration process for recycling fluids in multi-stage parts washers. So let's start by talking about diffusion dialysis acid recovery systems. So the consequences of improper disposal of acid waste can include environmental hazards, as improper disposal can lead to soil degradation, water contamination, and harm to aquatic ecosystems. Such pollution can have long-term ecological consequences and damage biodiversity. In the workplace, acid waste introduces significant hazards, as exposure to acidic substances can cause burns, corrosion of equipment, and dangerous reactions that increase the risk of fires or toxic emissions, jeopardizing worker safety. Also, failing to manage acid waste properly can result in regulatory compliance issues. Strict environmental laws govern acid waste disposal, and violations can lead to heavy fines, operational shutdowns, and reputational damage. Waste of many acids can be recovered for reuse, but without proper systems in place, these valuable resources are lost. So the solution here is implementing a diffusion dialysis acid recovery system, and that's which is one of the most effective methods of recovering acids for reuse. A diffusion dialysis acid recovery system is a membrane-based separation technology. In these systems, acid waste is passed through a specialized diffusion dialysis unit containing semi-permeable membranes. These membranes allow acids to selectively diffuse through, separating the usable acid from the impurities in the waste. The recovered acid that has diffused through the membrane is collected, ready for reuse in the production process, while the remaining impurities and waste can be safely disposed. So the system as a whole works as follows. The used acid is metered through the system and is in contact with one side of an anionic exchange membrane. Water is metered in a countercurrent fashion on the recovery side of the membrane, which causes the majority of the acid to migrate through the membrane, rejecting contaminants such as heavy metals along the way. The purified acid and water is directed back to the process tank, while the contaminated spent acid stream continues to the metal recovery waste treatment for further processing. Fresh acid in proportion to the unrecovered amount is added to the bath to maintain the concentration within the correct operating parameters. So the use of diffusion dialysis acid recovery systems helps to recover acids and reduce hazardous waste resulting from acid contaminations. This leads to multiple benefits, including protection of the environment from the acid waste, resource recovery, maintaining compliance with regulations, and overall financial savings. In one example, an Illinois manufacturer of stainless steel fittings and flanges had great success with acid recovery using a diffusion dialysis system. The company operated a 1,500-gallon pickling bath composed of nitric acid and ammonium bifluoride. Every 6 to 8 weeks, or about 7 times per year, the bath depleted and had to be recharged. As a result, the business incurred an annual cost of $18,000 for disposal and $13,000 for fresh chemicals. So Engineers from the Illinois Sustainable Technology Center assisted them with the implementation of a diffusion dialysis acid recovery system, which allowed them to recover 86% of the nitric acid and 30% of the ammonium bifluoride, reducing the need to recharge the bath from 7 times per year to 2 times per year, proving to be a cost-effective and sustainable solution. The outcome of these changes will reduce disposal costs, reduce chemical costs, reduce pickling time, and decreased rework. Acid baths play a crucial role, especially in the aerospace manufacturing industries, with a variety of uses. Acid baths are used to remove rust from metal parts and prepare surfaces for further processing, such as welding or coating. Also, acid baths with certain acids, like nitric acid, can be used to increase corrosion resistance of stainless steel parts in a process called passivation. So in a moment, we'll look at a couple of techniques that can be used to extend the life of acid baths. But first, let's discuss some of the risks associated with acid baths. Acid baths are comprised of harsh acidic chemicals. Improper disposal of used acids can result in environmental contamination entering soil and water and causing harm to the ecosystem. There are also safety hazards associated with the handling of these acids, including chemical burns, spills, and exposure to toxic fumes. These incidents are most likely to occur when changing the acid bath, and if an incident does occur, it could affect operations and delay or stop production. Additionally, OSHA has regulations that directly or indirectly govern the use of acid baths. So improper storage, handling, and use of these chemicals could result in penalties and fines. Finally, frequent replacement of acid baths can increase downtime of a process and will use significant amounts of these acids. Together, risks associated with acid baths can significantly increase operating costs and ultimately affect profitability. So one possible solution, instead of changing the acid baths when contaminated, the acid baths can be filtered and spiked with fresh acid. Filtration of the acid bath removes any solid contaminants that have accumulated, while adding additional acid to the bath will maintain its effectiveness. These methods together can significantly extend the life of the acid bath, in some cases making it viable almost indefinitely. So let's look at some of the benefits of filtering and spiking acid baths instead of frequent changing. First, this type of recycling of the acid bath can lead to a significantly lower volume of acid waste, which is beneficial to the environment. Next, there's resource savings. Filtering removes contaminants, allowing acid baths to be reused for longer periods, while spiking replenishes the chemical balance. This minimizes the need for fresh acid and reduces overall resource consumption. Also, extending the lifespan of acid baths lowers the cost of purchasing fresh acids and disposing of spent solutions, providing significant financial benefits. And finally, regular filtration and spiking can help with regulatory compliance. Properly managing acid baths helps meet environmental and safety standards while avoiding fines and legal penalties. A case study at an anodizing facility showed the effectiveness of the above-mentioned technique in extending the life of sulfuric acid baths. It was found that the facility was frequently sending used acid baths to the wastewater pretreatment facility. Before the application of acid life extending techniques, they were changing their acid bath partially on a regular basis and completely every 6 months. Annually, the company was spending about $3,000 to replace the spent sulfuric acid baths. With these techniques, they were able to reduce that number to about $1,000 per year. The $1,600 investment into these methods resulted in a savings of over $2,000 per year, meaning the implementation paid for itself within the first year and the company's costs were reduced significantly. This also represented more than a 50% reduction in sulfuric acid waste being disposed of each year by the company. So next, the next best practice we'll cover is implementing an ultrafiltration process for recycling fluids in multi-stage parts washers. Parts washing is a routine task within this sector. The parts often need to be washed after production to remove any oils, debris from machining, and other contaminants before they can be packaged and sold or installed. In the or in the aerospace industry, parts that are removed during maintenance or repair may need to be cleaned before reassembly to remove dirt, grease, oil, and other contaminants. Parts washing fluid, which is used in parts washing baths and can be water-based or solvent-based, but it becomes contaminated during the parts washing process and must be properly disposed of and replaced. So parts washing fluids come in two types: solvent-based and water-based. Solvent-based parts washing fluids are generally more effective at removing grease and oils than water-based solutions, but water-based solutions have improved significantly with time. Regardless of the type of fluid, it must be managed and disposed of properly. The contaminated fluid must be treated as hazardous waste and must be stored until it is ultimately disposed, and the disposal costs can be significant. If released without proper treatment, the waste fluid can cause substantial harm to the environment. While both types of parts washing fluid generate waste, the waste from solvent-based parts washing fluid is more challenging to manage. Water-based parts washing fluid is cheaper as it can be purchased in smaller quantities and diluted with water to fill the parts washer. Depending on the size of the parts washer, though, frequent changes of the fluid can result in significant consumption of water that will need to be treated as hazardous waste. Solvent-based parts washing fluid is more expensive and must be purchased in larger quantities since it is not meant to be diluted with water. Solvent-based parts washing fluid, being solvent-based, is more dangerous to the workers than the water-based fluids. Either way, there are substantial costs involved. So one possible solution is to filter and reuse the fluid instead of just disposing when it becomes too contaminated. Ultrafiltration technology can be used to remove contamination from the washing fluid, allowing the fluid to be reused. In the ultrafiltration process, the waste, in this case the used parts washing fluid, is sent through a membrane under a low pressure. The membrane filters out all but the smallest molecules, ensuring that most or all of the contaminants are removed from the used washing fluid, allowing the fluid to continue to be used. This technology was originally designed for the food industry, but advances in filtration technology and the development of stronger membranes made it appropriate for use with parts washing fluid. These stronger membranes, such as polyvinylidene difluoride, can handle industrial process solutions with high pH levels, elevated temperatures, and high oil concentrations. Ultrafiltration is regarded as a top technology for extending the longevity of various process solutions due to its unique capability to concentrate oily waste and produce clean permeate. The use of ultrafiltration to extend the life of parts washing fluids comes with several benefits. By extending the expanding the life of the parts washing fluids, the amount of parts washing fluid used and waste generated is reduced significantly, which has environmental benefits. Additionally, the waste generated from the removed contaminants is condensed, allowing for easier storage and disposal. When water-based parts washing fluid is used, extending the life of the fluid will conserve fresh water. Additionally, if a continuous closed-loop ultrafiltration system can be implemented, the fluid in the bath can remain fresher. This, along with the reduced need for fluid changes, can improve operational efficiency. The benefits from implementing an ultrafiltration system can result in significant cost savings from reduced need for parts washer fluid, reduced labor, and reduced disposal costs. And finally, in this section, we'll briefly discuss the use of eco-friendly products. So let's discuss Green Seal certified products as a P2 best practice in the aerospace sector. Cleaning and degreasing agents, adhesives, and paints are commonly used within the industry and unfortunately, many of these products contain harmful chemicals. Products like adhesives, paints, and cleaning agents commonly used in this sector can often contain harmful chemicals such as formaldehyde, 1,2-dichlorobenzene, and alkyl phenol ethoxylates. These substances pose serious risks to both worker health and environmental safety. For workers, exposure to these chemicals can cause a range of health issues. Many of these products contain chemicals that are volatile organic compounds, causing a range of health effects from eye, nose, and throat irritation up to liver or kidney damage, or even cancer. These chemicals can also impact the environment, contributing to hazardous emissions and pollution. Fortunately, there are safer alternatives available. However, it can be difficult to identify safer products among the many available options. So the solution then is to find products that are certified safe by reputable organizations. One such example is Green Seal. Green Seal is a nonprofit organization that sets rigorous environmental and health standards for commercial products, ensuring that they are safer for both the workers and the environment. Green Seal maintains key standards for each category of product, and products must meet the key standards for their product category to be eligible for the certification, which allows them to use the Green Seal certified logo. For example, G36 or GS36 covers adhesives, GS43 applies to paints, and GS34 focuses on cleaning agents. And these are just some of their key standards. So Green Seal certification guarantees that these products are low in toxicity and free from harmful substances like 1,2-dichlorobenzene, alkyl phenol ethoxylates, formaldehyde donors, hazardous air pollutants, and heavy metals such as lead, mercury, cadmium, hexavalent chromium, and antimony in environmental form or compounds. Also, Green Seal certification ensures that the products have low VOC emissions, improving both air quality and worker health. Additionally, these products are formulated with eco-friendly ingredients and must meet sustainable packaging standards, reducing their overall environmental impact. So by choosing Green Seal certified products, businesses can reduce harmful exposure, comply with environmental regulations, and create a safer, more sustainable workplace. So choosing Green Seal certified products helps protect the environment by reducing hazardous emissions and pollution. They support regulatory compliance, cutting the risk of fines and penalties. And finally, they enhance worker safety by minimizing exposure to toxic chemicals, creating a healthier and safer workplace. So, in summary, in this session, we discussed several PDU best practices that can be implemented in industries within the aerospace products and parts manufacturing and maintenance sector. But some of these are going to be applicable outside of the sector as well. These best practices can help you save money, improve worker safety, and protect the environment, ultimately contributing to a more profitable and sustainable business. So I hope that you'll find something from this webinar that you'll be able to take with you to help toward the objective of pollution prevention. So for more information on any of these best practices, including technical assistance, please reach out to myself or Dr. Ashish Nambarte. Also, please feel free to reach out to us for any other information or assistance related to pollution prevention as it applies to the NEAs or other industries, and we'll do our best to help you out. These are the references from this presentation.